Welcome, friend, to a quiet corner of the night where the world hushes itself into a soft murmur and the gentle light of your screen becomes a small harbor for rest. Tonight, you can imagine yourself settling into a comfortable position, your breathing steady and unforced, while we take an unhurried walk through a slow and soothing idea. The sleepy computation of a neuromorphic chip, where electrons do not rush, they meander, and thoughts are not commanded by clocks, but unfold like ripples across a pond at dusk. How sleepy are you on a scale of 1 to 2? If this soft wander through science helps you unwind, feel free to like this video and subscribe. And if you want a gentle stream of calm learning to carry you into sleep, the playlist link in the description is waiting for you, ready to play in a peaceful sequence as you drift. Imagine a quiet laboratory after hours, where the overhead lights have dimmed to a considerate glow. The benches are tidy, a hint of antiseptic and cool metal in the air, a touch of ozone from equipment that is powered but tranquil. A small chip rests in a socket on a simple board, surrounded by capacitors and resistors that look like miniature pebbles in a still garden. A faint LED gives off a blue haze, not intrusive, just a dim star in a private sky. The chip itself is tiny, an unassuming square of silicon and metal that is a little like a puzzle box and a little like a garden. It is both rigid and strangely alive with potential, ready to compute the way a breeze passes through reeds, by tiny impulses, by events, by soft, intermittent activity instead of a strident drumbeat. You settle in and picture gently what usually happens inside the computers you know. A clock ticks. It is a precise and constant metronome, a ruler that transforms time into the spaces between clicks. Everything inside that computer waits for that beat, aligning movements with it, like a whole orchestra watching the conductor's baton. There is a bus. There is memory over here, processing over there, an arrangement that moves data back and forth as if the mind were stored in one room and action in another room, and messengers run in between. It is powerful and familiar, practical and proud. But the rhythm, as steady as a marching band, leaves little room for the gentle hush we are cultivating. It can be fast, but tonight, speed is not our goal. Now, imagine something else. Imagine a system that does not march by a drum. It breathes. It does not count time to move. It moves when something happens. This is the quiet philosophy of a neuromorphic chip. It mimics the structure, not the fine details, but the overarching structure of biological neural circuits. It invites the world to speak, not in continuous flood, but in sparse sparks. Where a classical computer uses zeros and ones in waves based on timing, a neuromorphic system listens for little clicks called spikes, tiny events that travel through a network like delicate fireworks, though far gentler, like the small crackle of grains of sand shifting under a slow tide. The chip does not ask if the time has come. It notices in a soft and unhurried way that an event has arrived, and then it responds. In your mind's eye, the chip's surface stretches out into neighborhoods of neurons, each one a small circuit with a purpose. These are not neurons in the literal biological sense, but their behavior rhymes with that natural pattern. A little current trickles in, and the neuron circuit sums it softly. There is a leak, a gentle forgetting. If the sum reaches a threshold, a spike is produced, a small event, a whisper to its neighbors that something has happened here. The whisper travels along a sparse set of connections, the synapses of this artificial landscape. Each synapse has a weight, a preference for how much it will amplify or soften the message. If the weight is strong, the receiving neuron feels a firmer nudge. If weak, it receives only a faint tap. The receiving neuron adds this to its reservoir, and if the cumulative patience of the moment pushes it across its threshold, it whispers onward. No single whisper needs to be loud. The picture is one of quiet accumulation, of soft contributions and gentle dissipation. You might imagine this process as tiny lanterns lighting up in a slowly meandering procession through a garden maze, each lantern noticing the light of its neighbor and deciding whether to glow for a moment in acknowledgement. Time is not told by a clock, but by the occurrence of each glow. If nothing happens, the garden rests in darkness, serene and untroubled. The energy saved in these resting pauses is part of the charm. Neuromorphic chips, by virtue of being event-driven, can slip almost into silence when there is no activity. Nothing is spent on waiting, and waiting is so often what produces heat and noise. In this garden, stillness is not a state to be fixed. It is a living pause. It welcomes the ambient quiet. The materials involved in this miniature landscape are familiar to engineering, but their arrangement gives them a character that feels grounded and organic at the same time. There is silicon, polished and imprinted with a labyrinth of pathways. There are transistors that act as gates, allowing or blocking the flow of charge in a way that produces simple operations. There are capacitors that hold a small memory of the moment, and resistors that shape the flow like the narrowing of a river channel. There are interconnects laid out like roads in a night city. If you were a traveler the size of an electron, you would stroll along these roads without hurry, following signals that arrive when they have reason, and drifting through the calm wards of the chip when they do not. In some designs, tiny non-volatile devices called memristors gather in crossbar arrays, their conductance reflecting a learned preference, like a path that becomes smoother and straighter after many gentle footsteps. In other designs, dedicated memory banks store synaptic weights, and address event lines convey the news of a spike with very little fuss. These choices are engineering decisions, but the mood they create for us tonight is the same, a quiet landscape designed to respond softly and naturally to the world. You can feel the air in the room where this chip is tested, just a little cool, with a barely audible hush of ventilation that sounds like a distant sea. The lab chair is still. The bench is a soft mat of ESD-safe material, slightly rubbery to the touch. A scope sits idle, its screen dim, but ready to show small pulses and graceful curves. When the chip is powered, there is no fan roar. There is only the faintest of clicks from a relay, and then serenity. You are not watching a spectacle. You are watching the way information can gather itself into a murmur, and how that murmur can compute slowly and efficiently with no need for thunder. This is the sleepy computation of the night, where a little means a lot, and silence means everything. In this way of thinking, data is not a constant stream. It is a series of moments, An event camera, for example, does not capture every pixel at a fixed frame rate. It reports only what changes, like a person in a quiet room noting when a curtain moves. Paired with a neuromorphic processor, the world becomes a conversation of changes rather than a recording of everything. This is particularly soothing to consider at night when outward noise reduces and every small movement becomes meaningful. A simple neuromorphic circuit can listen to those changes and learn to respond. If a small line drawing passes by, if a sound chirps, if a scent sensor flickers, the chip collects these events and shapes them into patterns that can be recognized. The recognition is not based on a single loud instruction. It finds its way through repeated, patient nudges along those synaptic pathways. Some neuromorphic chips embody spiking neural networks with learning rules that are local and gentle. In the biological brain, one such principle is called spike timing dependent plasticity, a careful way of saying that when a presynaptic spike tends to arrive just before a postsynaptic spike, the link between them strengthens. And if a presynaptic spike lingers and arrives after, the link weakens. The neuromorphic analog chooses to approximate this, often in simple, energy-efficient ways, so that learning does not require a central registry of instructions. Each connection, each synapse, quietly adjusts itself based on the coincidence of events it experiences. You can watch that process in your imagination like dew gathering on a leaf. One drop at a time, each droplet a trace of what the leaf has met in the air, the accumulation soft and inevitable. The network tunes itself to the gentle statistics of its world. There is an elegance to the way these chips handle time. Rather than slices of a global schedule, time is local and also relative. To each neuron circuit, time is felt as the leakage of its membrane potential, as the delay of its refractory period, as the arrival of spikes with certain short latencies. The whole chip flows without a metronome. One area can be lively while another area is quiet, and neither interrupts the other. It is like different rooms in a house at night. In one room, a person folds laundry with slow patience. In another, someone else reads, the pages turning now and then with a very soft sound. In the kitchen, a light hum from the refrigerator, more or less steady. Each room has its own time, and the house as a whole breathes in a way that is more than the sum of its parts. If you look closer, you can imagine the neuron circuits with a threshold element, an integrator, and the synapses that feed them. The threshold may be set by a small comparator, the integrator a capacitor that stores charge in proportion to inputs. The leak is a deliberate path through which charge gently drains, making the neuron forget old events. The result is a simple and sturdy poetry of behavior. Inputs arrive as current pulses. The capacitor's voltage lifts, sometimes just a little, sometimes more. And when it crosses a threshold, a pulse is emitted and the circuit resets. This act of resetting itself is like a soft memory, a brief refractory pause that prevents immediate refiring. The rhythm is neither frantic nor forced. It is like a heartbeat in rest, steady and reserved. You might notice how many neuromorphic designs prefer asynchronous communication, When one neuron produces a spike, the event is assigned an address representing the source neuron. This address travels across an interconnect fabric, often following a simple arbitration protocol to ensure order without a heavy clock. It is called address event representation, and it is as delicate as its name suggests. Events whisper their origin and arrive where they are expected, with no more ceremony than needed. In a landscape of millions of neurons, the fabric's gentle traffic looks like fireflies finding one another in a meadow, a slow and spare exchange of signals that can go on all night without disturbing the stillness of the air. Imagine yourself holding the chip package, its surface cool and smooth, edges precise but not sharp to careful fingers. The pins or pads beneath are the only hints of how much connection this tiny square can make with the world. You bring it close to a socket and seat it with a soft click, one deliberate motion, a fitting that is satisfying in its certainty. When power flows, it is a whisper of current. If you could listen to current the way you listen to rain, you would hear not a downpour, but a soft sprinkle on broad leaves. The power consumption of a neuromorphic system is often measured in gentle units, tiny amounts for each spike, because the chip is spending energy only when it has something to say. When it rests, its draw is so small that it almost disappears into the background of the bench. This is part of the reason these chips feel like night companions. They prefer the calm. The tasks a neuromorphic chip likes are often those that suit the quiet. A sound detected by a microphone can be transformed into a stream of events that represent changes in amplitude, changes in frequency, content, changes in time. A small spiking network can learn to distinguish a gentle puff of air from a firmer one, a brief tap from a drawn-out stroke. A tactile sensor on a robot finger receiving sparse spikes from pressure changes can find the difference between fabric and paper, not by force but by pattern. The chip does not need to pull all information into one place. Each neuron understands only what is near it, and that suffices. The result is graceful and quite natural. It resembles the way you allow the weight of a blanket to tell your body where it is in space. A diffuse map of sensation that requires no central parade. When learning is needed, it can be implanted and trained in a variety of ways. Some systems learn offline, their synaptic weights tuned by an external method and then poured into the hardware like sand filling the grooves of a mold. Others, more biologically inspired, let learning occur inside the hardware using local rules so that each synapse adjusts itself based only on local signals, on the timing of spikes that pass through it, on little flags that tell it whether its partnership with a neuron was helpful to the pattern at hand. The training process in this world feels like the gentle repetition of a lullaby. Each iteration touches the network lightly and moves on. And over time, the melody settles into place. There is no rush. There is no need to hurry. Simplicity is not just a design goal, it is an atmosphere. Beyond individual chips, you might imagine several of them placed together, communicating through soft links, an array of neuromorphic units that share events. They form a larger system that never shouts. It scales by keeping the local passions local and letting the global effects be the sum of many small events. This is how a meadow becomes a meadow, not by a single blade of grass declaring itself, but by many blades growing quietly together, tuned to sunlight and rain. When you think of scaling in this way, it feels restful. There is no central stressor to worry about, no single clock that might hiccup and disrupt everything. Each part is right-sized for its role. Sometimes designers use mixed signal techniques. That means parts of the chip behave analog, like biological membranes and synapses, and parts behave digital, like address encoding and routing. The analog components give softness to the computation, a tolerance for small variations, a preference for power efficiency that comes from letting the physics of capacitors and resistors do some of the work. The digital parts provide crispness where it is needed, like signposts along a quiet path that are easy to read even in low light. The mixed character does not produce tension. It creates balance, a measured cooperation that makes the system both gentle and robust. If you peer farther back, you can imagine the creation of the chip itself. A wafer enters a fabrication line, gliding on conveyances beneath filtered lights. Gases flow and deposit thin layers. Light patterns imprint designs. Etching removes deposition adds, and the wafer slowly gains layers of meaning like sediment in a calm lake. The clean room hums with a constant soothing current of airflow. Operators move with deliberate calm, their garments soft and silent. What results is a set of patterns too small to see directly with the naked eye, but not too small to imagine. You imagine easily the regularity, the repeating tills of circuitry, the way each tile hosts a small community of neuron circuits and synapses, the way the metal interconnect glitters in the mind as if it were a sheet of frost. The wafer is then diced, tested, packaged, and shipped. And on some evening, much like this, it arrives in a lab where someone plugs it in, watches a few lights, and smiles, because the gentle garden wakes as it is supposed to, with nothing more than a whisper. In this environment, jitter and noise are not enemies. They are like the soft rustle of leaves that becomes part of the night's white noise. Analog variation makes each neuron slightly individual, each synapse a little quirky, and these tiny differences can make a network more resilient, more general, more comfortable with the unexpected. Biological systems seem to embrace this variation, and neuromorphic systems, trying to approach a similar grace, learn to let small randomness be a friend rather than a foe. Imagine 1,000 little candles, all the same in purpose but not exactly in brightness. When seen together, the light they foster is warm and consistent. The outputs of such a chip might be measured with sensors that translate spikes back into the world of numbers we can plot and evaluate. A scientist can look at rasters, which are pictures of spike times arranged by neuron. The way one looks at gentle rain patterns across a window pane, the clusters and gaps tell a story that is not violent, but precise. Over time, the rasters change as the network learns, and then they settle as the network becomes comfortable with the patterns it has been shown. The scientist may adjust a bias here, a threshold there, as if tuning a stringed instrument before a lullaby. The experiment unfolds over minutes or hours, not one tense episode, but a series of calm, deliberate moments, punctuated by the soft clicking of keyboard keys and the smooth movement of a mouse. If the chip is being used in an edge device, it might sit near a sensor on a quiet shelf or in a discrete housing on a wall, hearing or seeing events without intruding. It consumes so little power that it can stay awake all day and all night, listening without using more energy than a small nightlight. When it recognizes a pattern, it sends a tiny message, not a flood. It might tell an actuator to shift slightly, or a light to dim, or a system to save the event for someone to read in the morning. It does not wake the household. It does not disturb anyone's sleep. Consider a scenario in which the chip listens to the flow of air in a narrow duct. Turbulence creates little fluctuations, and these produce events in a sensor. The chip learns the normal pattern of the flow and rests in it like a cat that has learned the sound of its owner's footsteps. When something unusual happens, the chip notices, not as a shock, but as a deviation in a familiar pattern. It lets a larger system know with humility and then returns to observation. In another scenario, the chip connects to a tactile array on a prosthetic hand. The spikes from those little tactile sensors make a music that the chip can interpret into gentle commands, allowing grasping with a light touch. The hand does not squeeze. It cradles a cup of water, a page of a book, a delicate stem. The computation behind it is event-driven, efficient, and patient. Neuromorphic computation often reminds us that intelligence can be realized through distributed, local operations. Each unit works with what it has. The world reveals itself through coincidences of events. Patterns emerge without central oversight. This is a restful thought. In the quiet, you can sense your own mind doing something similar. You are not a centralized executive center issuing orders to each part of your being. You are a gentle country of processes, each handling its small domain. As you breathe out, you might feel how pleasant it is to relinquish the idea of control, to let gentle processes run themselves. Although the night is calm, the science we are drifting through has depth. There are models of neurons that incorporate adaptation, where repeated spiking slightly changes thresholds or leak rates. There are synapses that prefer to depress slightly with rapid inputs, or to facilitate, an elegant way of saying that the chip can be sensitive to the tempo of inputs, not just their count. Different time constants can make the network attentive to slow changes or quick ones. These design choices form a palette. The engineer paints with them, not in primary colors, but in soft tones and gradients, building a temperament for the chip that suits the tasks ahead. There is beauty in the mathematics behind this world. A neuron integrates a weighted sum of inputs and emits a spike when a function of that sum crosses a boundary. The synapse updates can be shaped by curves that decay with time, with lapsing tails that reward near coincidence and forget distant events. Networks settle into attractor states, which is a formal way of saying that their behavior gravitates to stable patterns. In the lab, those patterns might correspond to categories, to memorizable shapes, to routines. In your imagination, These attractor states feel like comfortable positions on a couch, places your body knows and returns to because they require less effort, because they feel natural once learned, because the cushions have remembered you. Traditional software can emulate this kind of network, but the emulation uses the loud rhythm of a clock to copy a quiet process. It mows through cycles, even if many cycles are spent waiting. It obliges you to compute every neuron state at every tick, even if most do not change. A neuromorphic chip, by listening only to events, reduces the computational burden to what is necessary. It moves when prompted. In a world of limited energy, which is all worlds, this is wisdom. It is a night owl's wisdom, conserved and precise. If you imagine yourself walking through the building where this research is being done, you might pass a poster on the wall that shows chips, named after brain parts or neurons. The papers have gentle diagrams showing the flow of spikes and the arrangement of synapses. There is a quiet pride among the researchers, people who spend their days designing circuits that do not demand attention. Some of them like to build their own small networks in spare hours, the way people knit, a craft built on repetitions and minute adjustments that lead to a whole. They might hook up microphones or small touch sensors and teach a network to recognize a familiar pattern, a whistle, a tap, a simple melody. They watch it learn not as a dramatic moment, but as a string of small improvements. The most satisfying part is often the silence that follows, the sense that the network has settled into a comfortable groove. The tools used to tune such networks are, themselves, gentle. A bias current can be adjusted ever so slightly to change a neuron's excitability. A threshold can be moved low or high. A leak can be tweaked, adding a small measure of impatience or patience to a neuron's nature. The synaptic weights can be warmed or cooled by small learning rates. This is like tending a bonsai. You trim here and there. You watch how the plant responds over seasons. You accept that growth is not forced. You adjust with respect. And when the shape arrives at something pleasing, you stop and you let it be. The history of neuromorphic computing spans decades, and its evolution has been deliberate. Each generation of chips has moved gently toward greater scale and lower power, incorporating lessons about how best to route events, how to balance analog and digital, how to integrate memory near computation so that data does not have far to travel. Memory near computation is soothing for energy. A synapse that stores its weight close to where the spike arrives does not need to fetch it from a distant store. The energy saved is like the difference between a conversation held side by side and one shouted across a field. Proximity has comfort. You can imagine a set of chips arranged like a tiled floor, each tile a small neuromorphic region. Events travel from tile to tile only when needed. The communication is sparse. Most activity stays local, and this reduces energy use while preserving the ability to compute patterns that span regions. The result is a system that even at large scales hums at a low volume. It stays cool. It is satisfied with its efforts. The outward world does not notice it working, which is the most polite kind of intelligence. In the soft twilight of your mind's room, consider how memory feels inside such a chip. Instead of being a separate bank of pages to be fetched, memory is distributed through the weights of synapses changes in tiny conductances, stored locally in places designed for them. Retrieving memory feels less like travel and more like stirring. If a familiar pattern is presented to the network, activity arranges itself along paths that are well prepared, the way water finds the bed of a river it has carved over many seasons. There is a relief in this. It shortens the distance between recognition and response, a courtesy to energy and time. Some neuromorphic chips use memoristive devices as synapses, elements that remember how much current has passed and adjust their conductance accordingly. These tiny elements can keep their state without power, and they change with small pulses. Picture a crossbar of such elements arranged in rows and columns, each junction a quiet, variable resistor that remembers. Training writes soft pulses to this matrix, sculpting the conductance landscape until the network begins to resonate with certain patterns. Reading involves only slight movements, a gentle probing, so that state is not disturbed. The matrix at rest just is. It resembles a page of music that does not sing until a bow passes over the strings, yet knows its notes just the same. In the tactile rhythm of this narration, you might feel a calm repetition settling in. The chip waits, an event arrives, the network responds, silence returns. It is the rhythm of a lighthouse at a distance, a soft pulse of light at intervals, the sea otherwise dark and sea. This rhythm can be shaped by design parameters that mimic living tissue, adaptation currents that build up and subside, inhibitory neurons that curb overexcitement, excitatory neurons that pass along input. The interplay of excitation and inhibition maintains balance, like the push and pull of waves that smooth the shore. Even the routing of events in such a chip has a gentle aesthetic. Packetized addresses traverse narrow lanes. Arbiters mediate without fuss. If two events arrive at once, a simple protocol decides who goes first, and the other waits briefly. No one shouts, no one barges. Over time, back pressure signals can slow certain areas, allowing others to catch up. The network learns to breathe with the pattern of its inputs. If the world speeds up, it adapts. If the world slows down, it settles. This is a computation style that respects what is present. You may now find yourself feeling the same pattern in your own body. There is a rhythm to the breath. There is variation that does not disturb anything, a small irregularity that is natural and kind. Your muscles are allowed to rest even as your ears hear the quiet flow of words and your eyes soften. You can think of the chip as a small companion in the night, not competing for attention, not demanding anything loud, but sharing a way to think that is aligned with rest. When neuromorphic chips are tested with sensory inputs, the encoding of those inputs becomes part of the art. The world of event cameras, with pixels that report change, pairs elegantly with spiking networks. The world of bio-inspired sensors, like cochleas that transform sound into spiked trains across frequencies, or olfactory sensors that abstract sense into intermittent spikes, pairs easily with this architecture. The sensors produce events that are sparse when the world is calm. The chip responds with activity that is similarly sparse, and in that pairing, the overall system conserves energy and stays cool. Heat is the friend of wakefulness, effort, and command. Coolness is the friend of rest. Sleep-friendly systems avoid unnecessary work. Neuromorphic chips go farther. They reward calm with calm. They become almost still. And when still, their power draw is as gentle as a breath. If you imagine them on a battery, you can imagine the battery lasting a long time. The chip is content to let time pass, checking only for events. If nothing happens, nothing is done. This deep idle is not inactivity. It is readiness without strain. In networks where learning continues during operation, there is a concept of homeostasis, a quiet balancing act. If neurons fire too often, their thresholds adjust upward slightly. If neurons are too quiet, thresholds lower. The network maintains a healthy diversity of activity, avoiding collapse into uniform silence or feverish chatter. This is reminiscent of the body maintaining temperature, of a room maintaining air freshness through ventilation, of an ecosystem allocating resources. The balancing is local. Each neuron adjusts to what it sees. There is no need for a loud director. This is a night-friendly concept. Everything that can be done quietly is done quietly. Beyond the basic spiking neurons, some systems host compartments within neurons, like tiny dendritic branches that process inputs with their own dynamics. This increases expressiveness without increasing volume. It is like adding soft harmonies to a melody. The overall effect is richer, but no louder. Similarly, inhibitory interneurons add structure to the flow, creating oscillations and rhythms that support pattern recognition. None of this is violent or frantic. It is coordination through grace. As the network solves tasks, you can measure success in peaceable ways. Classification accuracy can be recorded without fanfare. Inference latency can be short without being a race. Energy per inference can be small and pleasing. Engineers who appreciate these measures often develop a fondness for graphs that show low-power regimes, plots with axes in microjoules and microseconds, scales that affirm the modesty of the approach. They take comfort in how little is needed when a system is designed to align with the structure of natural signals. You can imagine, at this hour, a small neuromorphic module integrated into a wearable device. It listens to motion data, reading events from tiny inertial sensors. It learns your gestures and can recognize a tap, a wave, a turn of the wrist. The device does not constantly stream numbers over a noisy link. It registers only meaningful change. It can sleep when you sleep. In the morning, it is already there, attentive, without having been restless. Another picture forms of a small autonomous vehicle, perhaps a rover, perhaps a micro-drone, moving through a dim indoor space. Its cameras do not capture frames at fixed rates. Instead, they report edges and movements. The neuromorphic processor on board uses spikes to map the environment, to avoid obstacles, to control motion. It can be responsive without being computationally expensive. The battery lasts longer. The motors receive smooth commands. The vehicle moves like a creature that is just awake enough, not stressed, just responsive. Still awake? Comment the secret word, nebula. As the gentle narrative continues, let us slow further and rest on the sensation of material and shape. The chip package, if you hold it after an hour of operation, remains cool to the touch. The board beneath it is matte and patterned. The traces look like tiny rivers flowing to and from the chip's pins. An oscilloscope probe, if placed on an output pin, would show pulses, small rectangular shapes that appear in time as if someone were tapping the surface of a pond with a fingertip now and then. If you capture those pulses and plot them, you see the rasters, the rain. Another instrument might measure current draw over time. It would draw a gentle baseline, drifting up slightly when activity increases, drifting down when the network rests. There would be no dramatic spikes. Just the ebbs and flows of a contented circuit. A thought occurs about robustness. In many chips, variability and temperature changes can cause unpredictable behavior. Neuromorphic systems, by design, are tolerant of such changes because computation is spread across many units, and because the units respond to events with a limited range of behaviors, small drifts are absorbed. Learning rules, if active, can correct biases slowly. Even if learning is not active, redundancy distributes risk. This is part of why these systems are so appealing in uncertain environments. They are never brittle. They are reed-like, bending and recovering, content to find a new balance when pushed. Those who study this field often speak gently about trade-offs. They acknowledge that neuromorphic systems are not always the best fit for every task. Some tasks prefer numerical precision that is most easily obtained through synchronous arithmetic on digits. Some require large memories and complex control that the von Neumann architecture delivers with assurance. But when the tasks are event-driven by nature, when low power is treasured, when local processing is sufficient, a neuromorphic chip becomes a friend. There is no antagonism in this view. There is complementarity, like different tools on the same well-kept bench. Consider once more the way synaptic change is stored. In analog systems, the storage can be in trapped charge, in resistive state, in phase change of materials, in a transistor's bias condition. Such states change gradually with pulses, let go slowly, or remain for long periods. These are not heavy swerves, they are gentle curves. In digital systems, weights are stored in bits, which simultaneously gives crispness and makes change step-like. But if the step sizes are small and the update rules are gentle, the experience remains smooth. Over long periods, drift or aging is compensated for by refresh procedures that occur infrequently and unobtrusively, like reshelving books in a library at midnight. The interplay of structure and randomness is not just a design choice, it is an aesthetic choice. In nature, the brain receives random fluctuations in synaptic release and in background currents. It learns in that environment. A neuromorphic network, if kept too clean, may overfit. If too messy, may wander. But somewhere between these extremes lies a sweet spot of variation that supports generalization. Designers couple the system softly to small noise sources, letting them provide a dither that smooths decision boundaries and prevents rigid behavior. The result for us is a system that continues to feel like night air, gentle and slightly restless, never stale. You can imagine a real-time visualization on a screen in the lab. It displays a field of dots, each dot representing a neuron. When a neuron spikes, its dot lights with a faint glow, fading slowly. At any moment, Only a small fraction of dots are lit. The pattern drifts and settles, sometimes forming a shape that resembles the input, sometimes forming a stable arrangement that the network has learned to associate with that input. Watching this visualization can be restful. It is slow enough that you need not constantly track it. Your eyes can soften, aware of the glow fading in one corner and rising in another, like city lights seen from a distance. After a session of tinkering and learning, the chip's parameters are saved. The synaptic matrix is stored perhaps in on-chip non-volatile memory, perhaps off-chip in a little file that is small in size but large in personality. When the system is powered up again, these parameters are loaded and the network falls easily back into its learned habits. There is a comforting continuity in this. The chip remembers without effort. Memory becomes a part of the hardware's character. Imagine gently the future uses of such systems. Small, considerate devices that understand gestures and voices without sending data to far servers. Tiny companions that can interpret environmental cues for people who benefit from quiet assistance, like hearing subtle alarms in machinery and deciding whether they matter, or gently guiding a home's ecosystem to maintain comfort while using minimal energy. The computation that makes this possible is humble and distributed. The programming, if that is the right word, is experiential and local. Over time, these devices could become better by living quietly amid the signals they are meant to interpret. In the soft arc of the night, you feel yourself guided by recurring phrases and patterns. The chip waits, the world speaks in spikes, the network answers, and energy is spent only when needed. This is patience made into a circuit. The edges of complexity are softened by locality and tolerance, so that the chip need not struggle to be perfect. It can be good enough, and in being good enough, it becomes efficient. There is a harmony to this that feels humane. When evaluating such systems, researchers sometimes speak of energy per synaptic operation, measured in femtojoules or picojoules. These units are so small that they invite a smile. They are small like the movements of a sleeping pet, like the settling of a curtain after a breeze. When multiplied by many events, the total remains modest. The chip is frugal in a way that suggests quiet living. In a time obsessed with speed, there is something almost rebellious in designing for gentleness. But rebellious is too strong a word for tonight. What it really is a wish for alignment with the rhythms of the world that already exists. The neuromorphic approach avoids the bottleneck of transferring large volumes of data back and forth between a central processor and a memory bank. Instead, it keeps memory close and moves only events. If you have ever walked a long way across a house to fetch something and then walked back, you understand the energy cost of distance. If instead the thing you need is right where you use it, the effort feels minimal. This is the same courtesy brought to computation. It shortens the path so the mind can amble rather than sprint. When chips like this are deployed in larger systems, careful attention is paid to how they exchange information with traditional processors. The bridge between event-driven and clock-driven worlds is built with gentle buffers and compact protocols. The neuromorphic chip can send compact event packets at its own pace, and the receiving system can collect them in a queue and process them at its clock's rhythm. Conversely, batched data can be transformed into event streams through encoders that produce spikes at rates corresponding to values, a steady trickle rather than a flood. The bridge operates in a way that prevents either side from being overwhelmed. It is a careful handshake. Temperature variations are also considered gently. These chips often operate in environments without active cooling. Designers choose operating points and component sizes that give reasonable stability across temperatures. Where needed, circuits can calibrate themselves slowly upon power-up, like a person stretching after waking, establishing a comfortable range of motion before beginning the day's quiet work. Temperature sensors on the die provide hints to small adjustments that keep thresholds and leaks in the good zone. The chip stays composed. A person working with one of these systems might end a long day by saving parameters, turning off the bench supply, hearing the faint tick of relays again, and leaving the lab with the chip at rest. The building's late-night hush embraces the equipment. The quiet continues through the dark hours. In the morning, when power returns, the chip picks up where it left off. There is no sense of effort. The continuity is unbroken. This is fitting in a context that prizes graceful endurance. If you focus on the idea of plasticity again, the soft change of synaptic weights over time, you might notice how similar it feels to learning anything in your life. Repetition, gentle corrections, and renewal. Neuromorphic chips allow the possibility of on-device learning that happens bit by bit as experience accumulates. There is no download of a huge instruction. There is slow, situated improvement. That aligns with how we absorb patterns in the world, especially when we are not trying too hard, especially at the times like this when the mind is open and relaxed. The landscape of neuromorphic research is not limited to spiking networks. Some efforts explore more abstract dynamical systems implemented directly in hardware, compact analog cores that solve optimization problems through the natural settling of a network into a low-energy state. The system is set up to represent a problem in its parameters, and then the physical dynamics find the solution by relaxation, not by iteration. You could think of this as a marble rolling in a shallow bowl to the lowest point, a picture that is itself restful. The marble does not analyze. It simply yields to gravity and friction. In hardware, currents and voltages yield to their own internal laws and find a steady resting point that satisfies constraints. This is computation by letting go. Beneath all these specifics lies a philosophy. Many useful patterns in the world are sparse. They appear as changes against a background of sameness. Many meaningful correlations are local. They are seen most easily when processing happens near where data is generated. Many helpful computations are tolerant to small errors. They do not require perfect numbers, only good enough responses in time. Neuromorphic chips are built to embrace these principles, not in defiance of precision when it is necessary, but in acceptance that life is tolerantly precise. The chip you picture tonight is a gentle machine for a gentle approach to thought. As you breathe, picture again the arrangement of neurons and synapses on the chip, arranged in arrays or clusters, connected through simple routing elements. Each element is small and clear in its purpose. Together they create a fabric that can model patterns over time, patterns that unfold and dissipate, patterns that reoccur like the cycles of moonlight and tide. There is a comfort in knowing that complexity is built from many small, understandable parts. This comfort can settle around your shoulders like a blanket. In comparing neuromorphic systems to general-purpose processors, there is a story about clocks. The clock in a typical processor is like a heartbeat that never varies, an insistent tick that sets the tempo for all operations. It is necessary for its world. In a neuromorphic system, there is no single heartbeat. There are many little rhythms, each responding to conditions. Everything breathes in its own way. As the ecosystem grows complicated, it would be hard to find a single beat to satisfy all needs. It is easier and more pleasant to let each part choose its own quiet tempo. That is what happens inside the chip, and the result is a hum instead of a tick. A hum is easier to sleep near. The gentle hum is present even in the metaphors used to describe algorithms, where a conventional machine learning model may be trained through gradient-based optimization with clear, repeated iterations. A neuromorphic model might adapt in little increments, each spike learning rule applied as it comes, each small adjustment cumulative. Stochasticity plays a role, like a drizzle that moistens the ground in patches. But over time, the soil is refreshed overall. Weights settle into place in a diffuse way. No single change accounts for the whole. The picture of learning becomes an overlay of many small contributions. Consider inhibition again, the way some neurons' outputs decrease the probabilities of their neighbors firing or increase their thresholds. In networks, timely inhibition prevents runaway activity, introduces crisp boundaries, and allows for winner-take-all mechanisms where the strongest response rises and others yield. The most soothing way to imagine this is not as competition, but as curation. A group of cells takes turns. Tonight, one responds while the others rest. Toward tomorrow, the roles might change. Everyone gets to sleep sometimes. There is trust that the silence of one supports the clarity of another. This is a good moment to pause and imagine yourself leaning back, the weight of your head gently supported. The words continue at the same even pace. The chip in your mind continues its quiet computing, spikes appearing and vanishing like small stars behind a thin, slow-moving cloud bank. A train in the distance might pass with a muffled rumble, then fade. A clock elsewhere might tick, but only as a soft background noise. The chip, clockless at heart, does not notice. It cares only for events. If no events arrive, it prefers to rest. Designers sometimes talk about routing schemes for spikes that mimic postal systems. Each neuron is assigned an address and the spike is a letter. The network does not need to be fully connected. It needs to be connected just enough that messages reach useful destinations. Combining networks of neurons into hierarchies allows for complexity without the need for every unit to speak to every other. This is similar to human communities, where neighborhoods have their own chatter, and larger gatherings occur only when needed. Most of the time, most things happen locally. This keeps costs low and life manageable. The sensory imagery of a chip at rest might surprise someone who is used to thinking of computing as loud. But chips can be quiet and passive. Their life is not the noise of fans, but the slow persistence of a circuit that has found an easy balance. If you bring your ear close to the board, you hear very little, perhaps a high, stable whine from a regulator, a hint that power is present. You feel tiny warmth from a resistor or a regulator. The main chip, the neuromorphic coil, remains modest, a small island of function in a sea of silence. This quietness is an attribute more people seek as devices fill more of our spaces. It is good to have technologies that recede on the subject of memristors and other resistive memories. Their physics is, even in the details, a slow glide rather than a snap. Ionic motion, filament growth, and dissolution, phase changes, all respond to pulses with latency and inertia that give weight to updates. Hardware embodies memory not as a separate deposit box, but as a trace in the matter itself. There is poetry in that notion. The material bears the story of its experiences. Writing is not a burden. It is a response. Bringing all these thoughts together, you can now see a full picture. Sensors output event streams aligned to change. The neuromorphic chip receives these events and routes them to neurons that integrate and spike. Synapses weight these interactions and perhaps adjust themselves softly. Inhibition curates activity, and output spikes represent decisions which are reported quietly to whatever system benefits from them. No part of this picture has to be stressed. The frame rate is as low as needed, sometimes non-existent when the world is still. The chip is polite. It waits. Let us imagine, just for a moment, a creative exercise with the chip. A small microphone picks up the pattern of rain on a window. The event-based cochlea transforms this into spikes across frequency channels, each channel firing when its band hears a change in sound intensity. The neuromorphic network listens. It learns to distinguish the sound of heavy drops from fine mist, the first from the second, by the timing of spikes across channels. The learning rule strengthens synapses that precede network outputs associated with heavy drops. After some time, the network can label the pattern with gentle reliability. The demonstration is not meant to be dramatic. It is meant to be pleasant, to show that even subtle calming patterns can be recognized naturally by such a system. Now, a tactile scenario again. A finger with a small array of spiking sensors runs over fabrics laid out in neat squares, linen, silk, wool, velvet. The sensors emit spikes when small ridges pass beneath them. The neuromorphic chip listens and learns to associate the rate and distribution of spikes with each fabric. The experience is pleasing because it connects a physical feeling is to a computational approach that is equally soft. There are no harsh sweeps, no heavy vibrations, just gentle stroking and quiet spikes. To training, the finger can rest on the cloth, and the chip can tell, if asked, which one it lies upon. In this soft time, you can sense how neuromorphic thinking influences even human thought. Finding structures that minimize effort without losing function has a way of calming the mind. When you accept the event-driven structure of your experiences, you stop trying to fill every moment. You allow the gaps to exist and be beautiful. The chip has taught us that waiting can be power-saving. The night is a lesson in that everywhere. The absence of noise is not failure. It is an accomplishment. Engineers sometimes speak of the budget of a device. Each microjoule spent must be justified. Each milliseconds of latency is either treasured or unimportant. A neuromorphic system tends to allocate budget in proportion to meaningful activity. That is a form of fairness. A calm day costs little. A busy day costs more, but the cost is aligned with the task's demands. When designing for battery-powered operation, this fairness makes devices more predictable, and predictability is restful. You can plan for it and then not think about it again. Even the way the chip might sleep and wake is considered with kindness. If learning is active, the chip can keep some small state alive, but if not, it can power down deeper to a point where even more of its circuits go quiet. Wake-up can be triggered by an external event, a pattern from a sensor. The wake-up process is quick because the chip does not need to reload huge contexts. It sleeps lightly and wakes lightly, like someone who had learned to nap well. There is no grogginess. The memory of the previous day's patterns is present. In a wider sense, neuromorphic computing has a place in a family of approaches that includes analog computing, in-memory computing, and event-driven systems. The common thread is that physics is allowed to do some of the work. Instead of forcing operations into abstracted primitives that are only distantly related to the task, the hardware is shaped to align physically with the behavior of the computation. When physics does the work, it does so with the smoothness that comes from continuous quantities and natural settling. You can feel the difference in the tone of the lab. It is the difference between a loud factory and a craftsman's workshop at night. People sometimes ask about accuracy and compare benchmarks. The answers are often nuanced. Neuromorphic systems can perform well on tasks that match their strengths. On tasks outside their comfort zone, they may require careful interrupting and clever network design. But the story never needs to be dramatic. It is an honest acknowledging that tools have domains. Even with this humility, the field is full of quiet achievements. Drones that navigate using event cameras, prosthetics that provide tactile feedback, sensors that detect anomalies in machine rhythms, environmental monitors that classify sounds without wasting energy. Each achievement fits the theme. Useful, calm, modest. Pause now and revisit the physical details once more. The silicon die gleams faintly under a microscope's ring light. Through the lens, you see repeating patterns and the soft tones of different layers. You see bond wires arcing gracefully to package pads like frozen tiny fountains. The board's solder joints are bright and smooth. The connectors click into place with a subdued sound. Software running on a nearby computer prints logs in a quiet cadence, lines appearing at intervals, each a record of a decision or a status update. Each timestamp a reminder that time is passing in the easiest possible way. When the system is put away, the bench is cleared and the lab returns to its general stillness. The night is nearly complete. You find yourself at the edge of sleep. The neuromorphic chip, with all its small pulses and patient teensy circuits, has become a part of this evening, a companion that thinks with you in a way that does not disturb. The idea that a machine can be built to listen for only what matters and to do only what is necessary has a comforting simplicity. It echoes something inside you. That is why lingering on it has been so pleasant. If your mind drifts back to the comparison with traditional systems, the differences feel almost like different personalities in a library. The clocked processor is the diligent librarian who moves at a steady pace, checking every step carefully because the library has a schedule and responsibilities. The neuromorphic system is the gentle volunteer who comes in at night to arrange the newspapers and magazines that changed during the day, letting the rest alone. Both keep the place in order, but each in a different style. The night volunteer hears only the quiet, handles a few items, and then leaves a note. The morning librarian arrives to find order maintained without disturbance. In education, there is growing recognition that understanding does not have to be forced. Spaced repetition, low-pressure exposure, and incremental learning all align with neuromorphic themes. We can learn by allowing patterns to find us repeatedly over time, and we can rest in between. Tonight, we have let the patterns of this computing paradigm find us naturally, with plenty of pauses, with attention to the sensory details that make knowledge feel grounded. You might not remember every term when you wake, but the feeling of a different way to compute may remain, a wordless impression of patience, locality, and sparse activity. The final act of our slow journey is to dwell one last time on the simple loop of operation. The world presents itself as events. The chip receives and routes them. Neurons integrate and occasionally spike. Synapses wait and shape the flow. An output is produced when necessary. Then stillness returns. The gentle rhythm continues. If nothing arrives, the chip sleeps. If something arrives, it responds. In the same way, your mind can approach sleep. If a thought arrives, observe it and let it pass. If nothing arrives, rest in that quiet. There is no need to force anything. Let the room be dim. Let the air be comfortable. Let the sheets be cool and familiar. Thank you for letting this dim, calm exploration accompany you. If you are still here at the edge of sleep, you have been patient and kind to yourself. Let yourself return softly to your breath, to your body held by the bed, to the assurance that you are safe and sheltered. When you feel ready, allow your eyes to grow heavy and your attention to release. If this peaceful journey was comforting, a gentle like and a subscribe help this little channel continue to bring you quiet stories. And your support lets us keep releasing videos this often. Sleep well, and may the quiet computation of the night keep you company until morning.